Hello, my RF and microwave designers. Good afternoon, good evening, good morning, wherever you are. This is Dr. Mohamed Nezami again with another lecture on RF and microwave systems and devices design. As you may recall or have checked in my playlist or on my YouTube channel, there are various presentations on passive devices design and 3D modeling using ANSYS HFSS. We have, since then, we've stopped and we started a new series, which is the design of RF transceivers, designing and simulating modeling them using the Pathwave SystemVue package. This is probably the fourth presentation. We've done KU band LMBs, we've done KU band lockup converters, we've done L band transceiver for Inmarsat. And then today I'm going to present to you another concept, which is as important, which is KA band SATCOM lockup converter. Okay, this is basically the heart of the transmitter section of a SATCOM terminal. As you can see in the block diagram in here, here's the block diagram representation of one particular design that I architectured together. This is basically what we do. We take the L-band IF signal from 950 to 1950 in this case, or it could be anywhere from, say, 800 to 2100s, okay? And then we upconvert that, we block upconvert it, and thus the name block, to the KA band between 29 to 30 megahertz. Sometimes we extend it to 31, some systems. They've got SATCOM, KA bands, they've got military, and they've got civilian. The civilian one is this one here, 29 to 30. I think the military one is the one from 30 to 31, okay? So basically on this design here, this lineup design here, I've chosen it to be, you could say this is like either a block up converter with a large antenna, because the wattage out of this block up converter is only a little bit below 2 watts, okay? 1.5 watt to 2 watts, okay? And for today, this architecture is unique in the sense that it's a single conversion. Now, well, I want to avoid having to do double conversions, even though they make the filtering easier. But double conversions mean you've got two local oscillators, two up conversion stages, and that's a lot of complexity, and it's harder to do, so, and more expensive. So now in this system in here, which I will go in a minute with, basically we've got the, like I said, here is the IF section that is responsible to take the L band signal from the modem to the mixer, okay? And then we've got the local oscillator, which is just this section here, which is in this case what I'm doing to avoid the complexity of okay, like I was saying, the local oscillator that I've chosen today to reduce the complexity is we're going to use a synthesizer, a phase lock loop synthesizer that puts out a signal at 3.50625 gigahertz. That's easy to build. And instead of building a synthesizer at KA band, which is difficult, so what we're going to do is we're going to utilize frequency multiplications, harmonic multiplications. So we're going to take that, and then we're going to go into this mimic chip, HMC 370, and what it does, it multiplies ×4 the output of this, and amplifies it, of course. And then we'll go to the, and yet this is 4 times this, which is only 14 gigahertz. We need to get to 28 gigahertz as a local oscillator for this. So what I'm going to do is I picked this mixer, which is harmonically pumped. This is a mimic chip, Okay, surface mount MMIC chip, HMC 338. And this is a second harmonic pumped mixer, subharmonic mixer, meaning the signal you come in with a signal at 14, it internally actually emphasizes the second harmonic of the 14, meaning the 28.05, and it gives an IF out at the twice the 28.05 plus the IF in here. And then what we do is, since the image and the LO are so close to the upper sideband, really conventional with printed filters, there's no way, we just don't have a high Q technology to reject this sideband and the local oscillator. So what I'm going to do is I designed basically a step, a waveguide step as a section as a filter, meaning you use a waveguide as a way to filter out the lower frequencies, because it has a cutoff frequency and it has a very steep rejection. So I'm going to use just a small section of a waveguide just to reject the LO and the lower sideband, and that's the uniqueness of this design here. And then I'm gonna use a surface mount component in here, which is a bandpass filter that is from Knowles, or what used to be the Electric Lab. And so that is basically this filter in here is a brick filter, and it's good for harmonic rejection and out of band rejections. And then I have 3 stages of amplification. I use 3 stages. These are all gas mimic devices, okay? And so we've got the HMC 519 here, okay? And then the same device, I'm using it again. A final device, this is 1.5 to 2 watt device, which is a gas fit device also. This is the HMC 943. All of these devices are from Analog Devices. So, and that puts me out at a close to 2 watts, somewhere between 1.5 to 2 watts, depending on how hard you drive the IF in here. So what I have down here, this section in here, as you can see, this is just the, what I did is I modeled this stage alone, and I called it the RF stage, this one in here, okay? And then I took the IF stage, which is here, and modeled it also again by itself, which is here, to look at the various RF performances, okay? So let's start putting some theory, and then we're gonna go through the devices. We're gonna start, I forgot to tell you, the IF amplification, the IF filtering in here for the L band from the modem. I'm using a device that is from Mini Circuits, either a surface mount, a ceramic filter, or a lumped element filter, which they have it. So they have both. They have this filter here, which is 800 to 18 bandpass filter. And they also have this, which is 950 to 2200. And if you recall, this device is the same device I use in my video for designing the KU band LMB, okay, for the IF stage. And then, of course, I use a little driver amplifier in here to amplify the IF signal. Okay, it's a low noise amplifier. That's a PHEM device. And then, of course, we've got the mixer. This is the subharmonic mixer. And what it does, you got the LO signal, and you have an amplifier. This amplifier is tuned at twice the harmonic of that. So that's this filter here, which is a gas mimic filter, subharmonic. This is the device name. I have all the models for these, the system models. So, and that's what I put in this chain in here. So when you come in to this one here, for instance, this here, I didn't have the model. So what I did is I created my own IMT table. The IMT table is basically based on the data sheet, which I will show you in a minute. So it's based on the IMT table that is giving here. Okay, so they give you, this is the the IMT table, the M times N spurious outputs. And I believe this is an error, a mistake in the data sheet in here. This should say IF plus twice the LO, because this is IF minus twice the LO. Can't be this or can't be both. So they made a mistake in here. Okay. And then they left out also NLO, that's the LO harmonic number in here. They left out the label. It's nice to see an error in a data sheet. So this device is a nice device, and they give you all the information on it. So all the conversion loss throughout the device, throughout the frequency. So let's get back. So, and build up some theory, and then come back to the simulation model, okay? So again, my name is Dr. Mohamed Nezami. I'm an independent RF contractor. I design RF boards. If you have a design that you need to contract out, my rate is very inexpensive compared to the rates in North America and Europe. I operate out of Jerash, Jordan. You can reach me at this number using these phone apps, or you could email me on this email. So if you have a design, an RF board that you want to inexpensively develop, please let me know. Shoot me an email. I'll work with you on the specifications. We'll draft a contract, a design contract, and I'll deliver to you the whole system, the system design, the system model, the circuit design, circuit model, and then the schematic, and then the layout, the Gerber file. And I will also work with you during the testing and verifying and integration. Just if you have any issues, once you assemble the board and bring it back to your team, I will fly in to you and be with you at the design stages, if you like. So today's talk, like I said, we're going to talk about a SATCOM KA block up converter with a GaN power amplifier. I forgot. This is one thing I forgot. This here, this model that I built in here, which you will see, all of these devices are gas fit devices up to like 1.5 watts. But then, unfortunately, I didn't have time to finish it. But the objective was to design these using to further amplify the signal to get to the tens of watts. Because as you know, for SATCOM transmitters, reasonably on the move size dishes and flat panels, you need, say, from 10 watts to up all the way to 100 watts. And to build that, you need to go into GaN devices. And so on the next video, hopefully, I'm going to put out another video where I extend the power of this block up converter from 1.5 watt to 8 or 20 or 16 watts, which is more reasonably used for actual systems. Okay, so this is a device, for instance, from Curvo, and this device is a GaN mimic amplifier. It puts out 8 watts, and they give you the block diagram in here. And this is easy to build and integrate with the system that I'm designing today. Except this device has a huge gain, so you don't need to populate all of the devices, because you can see here, to get to 38 dBms, you need about only 12 dBm of power, which means I would have to come in here and exclude these 2 stages and just go from here, okay? All right, so let's continue on. So that's where the GaN device would be utilized. Just if you Google KA block up converters for commercial ones, you'll see plenty of these made out there. Now, why would you be interested to design your own? Well, sometimes you have a specific application where, for instance, you're trying to develop something different as far as frequencies, or as far maybe something cheaper. But you can see here, there's plenty of these. They come in all flavors and sizes and wattages, for anywhere from like 2 watts, 5 watts to 100 watts. They can come in as boxes like these or cylinders as these. These are cylinder size ones. So if you survey also the ground stations that these things go in, they're mostly for Ka band. You still got the large aperture ground stations for SATCOMs, ground terminals, but you also have plenty of applications where Ka band, a satellite on the move, or like these things from Intellian. You can see these ones, they use them a lot on boats, okay, on ships. But you can see the BUC here. You can see the BUC. Here's a cylinder BUC. Here's a cylinder BUC. These two people, they use the same, looks like this for the same one that is here, and that's from Mission Microwaves in California. As an example, I'm not trying to market for anybody. You know, I don't know these people. I'm not advocating any of these amplifiers, but just to show you that there's plenty of these. So let's get back to our design. So what we have an L-band signal that is between 950 to 1950. Usually from the L-band modem, this signal is low. Sometimes it can be as high as 0 dBm, but most likely you're going to get minus 10 dBm, and you want to put that out, like in my case here, I want to put it out at 33 dBm saturated. Okay, so we need to take the minus 10 and amplify it by at least 40 dBs to get to this level. And at the same time, we need to translate from this signal from these frequency block here between 950 and 1952, 29 to 30 gigahertz. Okay, so and the way to do that, of course, we mix the signal with the locally created oscillator signal, which is stable. Usually there's a phase lock loop that is referenced to an ovenized crystal. And then so you get a very low phase noise, very low jitter signal. And it is out of the scope to talk about designing these phase lock loops, but you could utilize these phase lock loops from various sources. You could either build it from discrete components, the ones from TI, Texas Instruments, or from analog devices, or you could buy it as a module, okay, surface mount module from various phase lock loop hybrid circuit makers, okay? So we mix, and in this case in here, because I didn't want to mix the L-band signal with a Ka band signal at 28 gigahertz, I want to operate at lower frequency and let the subharmonic mixer do twice the frequency of that. So this is, I set out with the 3.5, sort of like an S-band oscillator, and then I multiply by 4, filter out the harmonics, and then feed it to a subharmonic mixer, which pumps twice the LO signal. So what you end up with this signal in here, this would be the IF signal in here is twice the LO plus and minus the IF signal, okay? And then, of course, we do some kind of filtering in here. We have a two-stage filtering to reject the image and which is the lower side band, and as well as the local oscillator signal, because it comes in a strong signal. And then I have 3 stages of amplification, 2 of them, these 2 identical devices that build up the, this is a pre-driver, driver, and the final stage, okay? Now, so to do that, I took the RF and the IF sections by themselves, okay, and looked at them closely and designed them carefully, lined them up, and then put them back in the overall architecture system, okay? So starting out with the IF stage, okay, we take the L-band signal, we amplify it, and then we have to filter it because you never know what could come out of the modulator. Usually it's a clean signal, but we always want to assume the worst case. So we're going to go into one of these devices in here. Either this or this will do. As you can see in here, we're not particularly, as long as it passes somewhere between 900 to like 2200, either one of these devices from, these are low cost. This is way lower cost than this one. I think this module, this surface mount filter in here is about $30 each. This one here is like $5 or something. So you can cascade as many of these stages as possible. And of course, you get like about a dB loss throughout the filter. So this filter in here is used in the IF stage, okay, which is used right here. I'm sorry, right here. This is the IF stage. So we amplify. We have a pad in here just to control. Sometimes in some real systems, I've worked on one system where we used a programmable GaN amplifier in here, so that actually the system will come in and vary this level. But in our case, I chose to do it as a fixed IF level. So you come in from an L-band modem into an amplifier, we pad it down, we just to make sure that we have a good return loss. We start out with good return loss, and then we go into this filter in here. This filter has a very high rejection filter out of band like it is here. So you need to make sure that you have an absorptive piece in here. And then we pad it again before we go into the mixer. Okay, so that's the filter that we utilize, either one of those. And this is the response right now for the IF stages. Okay, this is starting out from my level in here. I set it out with -8 dBm. Okay, and so my final signal at the mixer is -1.38 dBm at this point here. Okay, which is typically, that's what it's almost a standard how people do this. And if you look at this here, just to assure myself that I will have linear response IF stage, regardless of the peak to average of the signal. So what I did is I backed it to -8 dBm, but this device in here saturates at about +17 dBm. So meaning we really have a huge, we are backed off by 20 dB from saturation on this device. So, which is good. That gives us a good IF stage to hit the mixer and make sure that we don't distort the signal before we up convert it to the final KE band. Now, the overall response of the IF stage is given in here, okay? And of course, we do have a slope that comes from the filter and the amplifier. The overall slope, as you can see in here, it's about a dB, I would say, okay? Now, how do you fix that? Right now, we're not going to try to fix that, but we fix that with equalizers, just a very simple passive combination of lumped components. We do that once we start the schematics, we include that in there. So we just make sure that we have some kind of, like say, a series inductor that will have a little higher, that will have a slope that is opposite to this, and it does equalizes that, okay? But we have to wait until you get to cascade the whole thing at the schematic level, and that's where you would model it again, including all the passives and the biasing in ADS, of course. Now, so let's get back just so we would recall. So basically, that was to cover just this section alone here. All we did is we covered this section in here, okay? So we came into the IF. We have the IF, which is, in this case, this is the response for the IF, okay? And so we have, this is the, as I said, the budget link calculation for the IF stage. And of course, this is the power sweep of the IF, okay? Another thing I did is I swept the IF with tones, multiple tones. So I swept it, and you can see how the system behaves. Again, this is very much giving me exactly the same thing, okay? And you can see that we've got the inner, okay, so next, what we're gonna do, so we have the IF up converted. So we're gonna talk about this section in here, which is the RF section, okay? And in the RF section, basically, what we have a combination of two filters, okay? One of them is, let me show you, one of them is this filter in here, Okay, this is a filter, the surface mount device filter that is from the Electrical Laboratories, and you can get this through Mauser. Okay, so this is a nice filter that filters the passband is from 27 to like 31 gigahertz. It's a nice. The only issue with it is that it the filter has a nice skirt, but then it goes up here and passes these frequency regions, and unfortunately, that was unfortunate to see. So, so let's just show you where that. So that's this filter. That's the filter, how it behaves. As you can see, it has a nice skirt that comes down, but then it bounces back up due to the dimensional of the filter, the resonances. You know, you got the second mode resonance in here that passes signal up here. So, oh, this is terahertz. Why is it not gigahertz? Okay, so you can see that it can filter out nicely to like 30 gigahertz, but then it goes beyond that. It goes to like areas below 40 gigahertz from 37 to 40. And unfortunately, the with this system that we have right now, the LO, which is in this case is a 28 gigahertz, the second harmonic of the LO and subharmonics of the LO, they can easily go up and pass that through that. So hopefully that gets rejected in the first filter, which is a waveguide filter. And let me just show you the response for that. Okay, so this is what you can see in here when you look at this. This is basically all it is a waveguide, really. A waveguide that was the dimensions of the waveguide were designed so that the TE10 mode has a cutoff frequency at around 28 gigahertz or so. Okay, well, around 29 gigahertz. So the LO is 28, as you can see here. The LO is down at 29 gigahertz. No, I'm sorry. The LO is 28 gigahertz. 28 gigahertz is down here, way down here, right here. And that's at around minus 94 dB of attenuation. So you can't really get this kind of filter response from any printed technology. So you have to have a waveguide filter to do that. And in this case, all I did is used in this system to reject the LO and the lower sideband is just use here, just a small piece of a waveguide that passes the desired signal only, that has a cutoff frequency below the lower sideband and the LO and the harmonics of the LO. So that's what we get, and that's how we get to reject all of these things. Now the RF response is shown in here. We have about 32 dBm if you drive it from, I think this was minus 12 dBm. We drove it. Yeah, that's the drive level. And so if you look at the CW tone sweep, this is what we got basically. Let's see, it takes some time. Okay, so again, we have the same slope. Okay, so the budget link for this chain, as you can see in here, we are in compression to get to 32 dBm. And so we're starting out with the pad that is after the mixer. This is this pad in here. That's this pad here. So that budget link is just for this section with minus 12 dBm at the output in here, because we drove the mixer with minus 1 dBm and it has about a 10 dBm conversion loss. So we're down in the minus 12 dBm in here. And so if you look at that chain, which is here, to get to the final PA, we do go in compression. This curve in here, that's for the composite compression. Let me just make sure that the labels are done. So we have a desired channel power, we have cumulative gain, we have the input 1 dB compression point and the cumulative compression levels. So to get to 32 dBm, we are compressed about 2.12 dB levels, okay? So you can see how nicely we can come in, and then we start gaining, reaching the gain. The overall gain for this stage here, the RF stage, is about 44, and we've got 6 dB in the IF, so that's about 50 dB, and we've got the mixer conversion loss is about 10 dB, and so we're down to the overall gain that we wanted to get from minus 10 dBm at the L band modem modulator to the 2-watt in here, or the 32 dBm. Okay, so let's get back to so what we do in here now. We're at the we said, so finish the IF. So the filtering of the sideband, I did it using a little section of a waveguide. And the way to do this is you basically have a cutout in the board, and you could design it using waveguide to BCB to microstrip transitions and have a waveguide that gets assembled to your board. But my objective in this is no, I'm going to go out of the board to the edge of the board to have an SMA connector in there, and then come back again at a physical distance that is long enough so that I can use externally connectorized waveguide section, small section. Or you could try, if you want to do a printed waveguide, which is a substrate integrated waveguide that has a response like this, which is exactly identical to a waveguide, and you can design that. So you could have the microstrip to SIW transition on both sides and utilize that as well. So I'll let you know if we ever get to build this thing. You will be notified with another video on this. So the LO harmonic of 14 gigahertz. Remember, we start out with the LO here being at let's see, it shows that. Okay, so we have the LO is at 3.5 gigahertz. So what we do then is we multiply that by 4 and filter it, and what we end up at the mixer point in here with the signal level is this, of course, and that's 14 gigahertz. Okay, now these harmonics are okay, they can go in and they interact and so on. And of course what we end up with, if you look at the IF signal in here, so we end up with this big spectrum, and of course all the subharmonic products, but we end up with one here, which is basically where the desired signal, which is at 29.5 gigahertz. Okay, and we can just ignore this stuff, and that's this value here. Okay, and the nearest ones are rejected way down. The lower sideband is not rejected yet, so it's going to be rejected further in the bandpass filter. So we go through that. That's the harmonic LO filter. And so next, we did talk about okay, so this is the budget link for the KU band RF section in here. So we covered that, and we showed that the green one in here is the 1 dB input compression point, which is minus 14 dBm. So we're operating at minus 8 dBm out of the L band. So that's 6.5 dB of margin, so which is good. The overall frequency response, we showed it, and again, we do have a slope that will be dealt with the once we on the printed circuit board itself. The signal, the way I'm driving right now is at because you do saturate at 32.2 dBm, and I'm operating at minus 12 dBm from the this chain in here, So you're decent. We have decent margins. Okay. Now again, like I said, this filter in here from the electric graph. It's a good, nice filter, but except it has this piece in here. Of course, we're going to solve that when we do the PCB layout. We're going to design, like for instance, to get this, I'm going to design an open stub. I could add an open stub that will basically notch out this region in here, because this is, it's really not desired, because we do have products, a lot of products that ends up in this region in here below 40 gigahertz. Again, the IF and RF tone swept signal for -8 dBm out of the modem. The L-band modem is shown in here, and we could see all these components. Again, like I said, the slope will be dealt with on the actual PCB design and the once we start picking. So where do we go from here? We can go now. What we have designed is, you can assume it's like the really the intermediate power level section of the block up converter, the BUC. So if you by the way, this design can easily be used also for 5G. As you know, there are some 5G systems that are operating in the Ka band. So this might very well work very good for 5G systems, because in there you don't need a lot of power. 1 watt is plenty for a lot of these macro cells. Okay, I meant macro cells, sorry, or small cell type coverage. But if you need to go further, higher in power, you have these devices that are available commercially, and you can buy them from Mouser. So these are all GaN powered devices. They're all MMIC, so they're really easy to integrate. We've got 5 watt device, you've got 4 watts, 9 watts, and 8 watts. So you can build as many as you want of these and end up with power levels in the excess of 100 watts if you like. Okay, so this was we have covered basically the design of a Ka band block up converter, 1.5 watts, from a modem, an L-band modem at -10 dBm levels. Okay, and so we went through the Pathwave SystemVue simulations of the system, and that's what we did cover. So let's just have a brief review of what we did. So we did a SATCOM lock-up converter with GaN power amplifier. We did a survey and showed that there's plenty of these commercial available out there. Why would you do one yourself? Well, you could do it as you're doing experimental work, if you do research work, or if you're trying to have introduce something cheaper. And so we showed how these systems go into the actual, these BUCs go into the actual systems. Here is the overall block diagram, the architecture that I designed for the one I'm proposing here, which uses an S-band synthesizer and a subharmonic, 2 times the LO subharmonic mixer. I'm utilizing a waveguide section to do the out-of-band rejection of the sideband and the LO, which is very challenging to do. And so I'm using a chain of 3 GasFET MMIC devices to build up from -12 dBm at the output of the mixer to the 32 dBm saturated level. I did an analysis for the subsections of it, which is the RF section, the IF section, all the corresponding filtering. We went through picking up the components that we could use for this design, like for instance, the IF filter topologies that we use commercially from mini circuits. All of this stuff you can obtain from Mouser and DigiKey distributors. By the way, another thing for those of you that are not in North America or Europe, if you have difficulty obtaining these devices, you can always go in and start doing searches and substitute for these using Chinese, Taiwanese, Korean, South Korean parts. These are, so there are some devices that could replace all of these if you want, if you have difficulty of getting these parts. We did go model the budget link for the IF stage, okay, and the power. We swapped the input from the L-band modem to the mixer and made sure that we are backed off, linearly backed off, so that we can have headroom for linearity. We looked at the frequency response of the IF stages. We did show the powerful impact of using a waveguide suction as a lower sideband LO rejection. Basically, instead of using a filter, we just use a piece of a waveguide that basically has a cutoff frequency right above the LO, so that we can utilize it to reject the LO and the lower sideband. We did propose that you can do this also with an SIW filter if you don't want to use mechanically assembled waveguide suction that has two SMA connectors on it, so that you have to transition out of the BCB to SMAs back and forth to get to the waveguide. We did show this is a hairpin filter designed for the LO to pass the ×4 the S-band phase lock loop signal, okay, at 14 gigahertz. We showed the overall budget length for the RF stages in here. And then we showed the frequency selectivity of the RF stage in here. We did show, and we showed that there is a slope, but that can be corrected with the with additional passives, passive equalizers at the IF stages. And we did utilize an off-the-shelf, commercially available bandpass filter, except that it does have an issue. So that issue will be remedied with the use of microstrip open suctions at these frequencies in here. Okay, ladies and gentlemen, so this was it. Like I said, my name is Mohamed Nezami. I'm an independent contractor for RF circuits and microwave systems. I have available training classes, basically 3 classes right now. I have one for the 3D modeling and using of designing microwave devices. You can go down to my videos, and all the videos that you see that were done on using ANSYS, we cover those in the training session, basically. You come in, you have your laptop, we give you the copy of the evaluation copy or the student copy of HFSS, and we get you started from 0 to the point where you can actually model all these devices that you saw earlier. And the cost is reasonable, okay? This includes staying at the hotel and the meals as well. We hold it at this hotel in Jerash, Jordan. We hold it 3 times a year, okay? Now, the other 2 trainings that I have one for SystemVue, which is like what you just saw. If you want to work that type of work, I have this session in here, the 3-day training using SystemVue on building transceivers and block level type modeling of RF systems. And then we have what's coming up in my next series, which is I'm going to be using ADS for the active parts and to actually do an actual complete BC board that contains the designs, that contains the devices, the passives, the microstrip work. And that's where you actually get into the real implementation of these things. So I thank you again. If you have any need for consulting, if you want to offload your department engineering from design work that you could outsource to me, I would welcome you to reach out to me at this number or at this email, and I'll be glad to help. Okay, and the rate is very reasonable, very cheap compared to the rates that are in the United States, even in India. I will compete with India. Okay, so you will get basically, I'll work with you on the system level specifications, system level modeling and designing, and then on the boards. I will turn in all the bill of material, the Gerber files, the schematics, everything, and we'll work with you on the produce the board and even testing. If you need to have my assistance in the final testing and integration, I'll come in on site and help you with whatever we design. Again, this is Dr. Mohamed Nezami wishing you all the good time. Thank you very much, and we'll see you next time. Thank you.